I'm going to talk about a really popular object in mathematics and in algebraic geometry, which are Hilbert scheme and their nested version. Hilbert scheme appear in many areas of mathematics. I encounter them because of the Moduli theory, but for example, they are related also to the on-fly polynomial that we're going to see in Tudor's talk tomorrow. So let me just start with, something similar to what we saw in the previous talk. Easier. First of all, a convention. So all curves that we will see today are integral and over the complex number. Indeed, many of the things I will say will also hold in the reducer and in the non-reducer reducible case. But for expository purposes, it's much better if we keep this hypothesis. Well, this is just because I don't like positive characteristics. So let's start with C, which is a smooth projective curve. So, if we consider this curve, we can associate to it a very familiar object which is the symmetric product. And the symmetric product, as we know, parameterizes, first of all, it's, basically because of Newton's theorem of symmetric function, it's a smooth projective variety of dimension n, and we can think of it in two ways. So, first of all, we can think of it as the variety parameterizing effective divisors on C of degree m. But also, we can think of it as the closed zero-dimensional subschemes of length n. And today, actually, we are interested in these objects and in their homology. Indeed, let me say now that we are defining, we will also be interested in their nested version, where when we have n plus 1 points and we fix the first n, okay? And similarly, if we want to consider them as subschemes, it means that we are just fixing a subscheme of colength 1. Okay, so we are interested in their homology, and as many of you probably know, the homology of the symmetric product is described by the famous McDonald formula. So if we want to actually compute the ith homology group, so for me homology will be with rational coefficients. We don't want any torsion, and this is actually the homology of the symmetric product just depends on a linear algebra operation that we're going to do on the H1 of our curve. So basically what we do is just take the direct sum from case that goes to 0 to the floor of I over 2 of the external power of H1. And then, since we want this to be a Hodge theoretic statement, possibly, we just add the state shift. Okay? And indeed, let me call SIM this linear algebra operation that we apply to H1. So similarly, if we want to consider this object, indeed, this is isomorphic to the product of the symmetric product times C. So again, it's sufficient to compose our linear algebra operation S with Kunet formula, and we get that the ith homology group of Cm n plus 1 is actually equal to a linear algebra operation that I call TIM of H1C. And this will be, the sum from J equals 0 to 2 of Ij of C tensor S I minus J of H1. course, this picture can work in family. So in particular...
When you write this, do you mean this as a Z2 graded space?
No, I mean a homology with rational coefficients.
Okay, so it doesn't depend on the parity. So in the maybe first formula?
What's the problem?
Never mind. Okay, sorry. Sorry, there's no I. I is not doubled. I'm sorry.
No.
K is doubled. Yeah.
No. Okay. So, of course, we can do this in family. What I mean is that I can consider a family, a smooth family, of projective curves over a base B. So, as we know, if we have this is a proper holomorphic vibration, so in particular it will satisfy our as one lemma, and we will have that all the fibers are diffeomorphic to each other. And indeed, this picture will hold if we replace H1 with our R1, which will be R1 pi star Q, which is a local system, which is with fiber H1 of CB, where here with CB I mean the generic fiber over a point B. Okay? And in this case, precisely McDonald formula will hold in the exact same way, but we are replacing this object by R1 and here, well, we consider the cohomology complex that computes the total space, the cohomology of the total space of the family, which is the higher direct image that we denote by R by star Q. So for Nazis of perverse sheaves and derived category, I'm using the bad numbering convention. So actually here I'm not putting the dimension. I'm centering intersection cohomology at 0. Okay? If you're not Nazi, you can just ignore what I've just said. Okay. So now...
And these linear algebraic operations are the same?
Yeah, the linear algebraic operations are absolutely the same. Indeed, we can also have that this is an R1 carries a mixed structure, and also this summand on the left carries a mixed structure, and actually the equality that we have here is an isomorphism of mixed structure. Okay, so we have seen that in the smooth case, everything is beautiful. Basically, these two statements that we can have here, let me call it, sorry. With here, I mean that I have to consider, I haven't been precise. Sorry, here I'm saying that given this family, I can consider the relative family of symmetric products and nested symmetric products. And you might ask, why am I doing that with square bracket if I'm talking about symmetric products? Well, because basically, in this case, we will see in a moment that this coincides with the so-called Hilbert scheme. What am I talking about? Let me emphasize. So in general, one might, so to understand why this smooth case is so beautiful, we need to understand what goes wrong when we have something which is similar. So indeed, now we consider C.
Sorry, I missed, what is R1?
Sorry, R1 is a local system on our family. So it's a local system on our base B, which has fiber, which is isomorphic to the H1 of any fiber, because they are all diffeomorphic. Okay? And with this linear algebra operation, we can describe actually the homology of the total space of the relative families of Hilbert scheme or symmetric product here is the same, and the nested one. Okay? So basically we can transpose the McDonald formula, the generalized McDonald formula that we had for one curve to a whole family. And this is basically the baby version of the famous decomposition theorem, and it's called, well, this is just due to the degeneration of the Leray spectral sequence of this mapping too. Okay, so now we consider C, which is a singular curve, integral, because all the curves today are integral. So as we said, we can still consider the symmetric product parameterizing the effective divisor, but this time, if we want actually to parameterize the zero-dimensional subscheme of given length, then we will have to consider the so-called Hilbert scheme. And this time, they are not the same thing, because take a curve with a node, for example. So actually, there are many subschemes which are supported on twice the nodes. For example, if I take the node which is the origin, I will have that all subschemes of type ax, by, x squared, y squared will be all supported on these nodes. So I have, in this case, I have a whole P1 of subschemes. If I consider, for example, C2 here. And in general, if I consider Cm of something like that, what I will get, it's like a sequence of m copies of P1. Okay, so they actually differ to each other. And there is this, it's called Hilbert homomorphism. And the same holds if I consider the nested version. The point now is that the McDonald formula still holds for the symmetric product, but now it doesn't tell us anything about the cohomology of the Hilbert scheme. So the question that we might ask is, can we recover the McDonald formula or a sort of McDonald formula for a singular curve? So the answer is yes, but it's done in a slightly subtle way. So the main idea is to actually include our curve, our singular curve, into a family. So the idea, the picture that we should keep in mind is that maybe I have like a base B. My curve is like a banana curve, so with two nodes. And in the family, I will have some honest elliptic curve, but I might have a curve with one node. So I will have a family whose fiber jumps. It won't be smooth anymore. Okay? And we make some requirements on this family. So we ask that the base is big enough, and we will see what big enough means, so that the relative families of Hilbert scheme, so we ask that V is big enough so that the total spaces of the relative Hilbert scheme and on the relative nested Hilbert scheme are non-singular. And for example, this can be done when B is what we call locally versal. So instead of writing like a precise definition, let me say in words what locally versal means. So locally versal means that I have a deformation of C which induces versal deformation of all the singularities of C. Okay? So if B is locally versal, for example, then there are theorems that are due to Vivek Schendel for the ordinary Hilbert scheme case and to me for the nested case that ensures that if B is locally versal, then what happens is that we have non-singular total space of the family of relative Hilbert or nested inverse schemes. And indeed, what does big enough means? Big enough means that, so the right condition is the following. So you will have your space, you will look at your space T1 of first order deformation of C inside here. And indeed, of the first order deformation of your curve, and you will have a map to the sum of the local T1 at the singularities. Okay? Moreover, if you have a family, you can also construct a family from the tangent space at 0, the most singular point, to the space of local deformation. And actually what you ask is that the composition is surjective. Let me remind you one thing, just to see that it's not given that the things go always right. So having the total space of the family, which is smooth, is not sufficient for having a smooth relative Hilbert scheme or nested inverse scheme. So for example, it's easy to find a counterexample. So for example, you take a curve with 2 nodes, and you can always smooth it out in a one-dimensional family, okay? So, but now let's consider the relative inverse scheme of length 2. So if we look at the tangents, so this one is a variety which has dimension 3 because it has a 2-dimensional fiber times the 1-dimensional basis. But if we look at the tangent space at P plus Q, then what you have is that you have 2 from this node and dimension 2 from this node, so you get 4. So it cannot be smoothed out in a 3-dimensional, I mean, it cannot be smooth because you are a 3-dimensional variety. So this one cannot be smoothed out by a 1-dimensional family. So you need to be a little bit more careful in doing that. Okay? So now what we do is to embed our curve in any such family which satisfies this condition. So we are sure that the total spaces of the relative Hilbert scheme and on the relative nested Hilbert schemes are smooth. Okay? So we have, and moreover, we will have, so we have our family here, which contains our singular curve, and possibly other things. But indeed, we will always find an open set, which we can, for example, call B tilde, in which we are in the same situation as before, so that indeed our family restricts to a smooth family. So let me call B tilde is open set, and pi tilde the restriction. Okay? So now, if we just consider the family, the tilde family, then we are in the same situation as before. So we can just write that our family McDonald formula for family, which means like, it seems like a slogan, but it's not. So we will have that R pi tilde Q is actually equal to, well, SID of R1 pi tilde star Q. And for the nested case, we will have the same. But we will have to change the linear algebra operation that we apply. Okay, so we have it on a smooth open set, but we are mathematicians. So when we have something on a smooth open set, our deepest desire is to extend it to the whole base. Okay? And the idea is that we can do that, but we will sacrifice something. So indeed, we know that if we want to extend this to this picture to the whole family, so to take out the tilde here, what will appear is indeed the so-called intersection complex associated to this local system. And here, instead of having an equality, we will have a proper inclusion. What I mean by that? So, for those who are not familiar with the intersection complex, let me just tell you this. So, the intersection complex, in a first approximation, can be thought as a local system with singularities. So the idea is that, for this particular example, is you have a map, you have a local system associated with this map, which is actually a local system on an open set, and you want to extend it. So this is like the closest thing that you can get to a local system, meaning that it's an object, it's a complex of sheaves, which is in the derived category of constructible sheaves, which coincide indeed with your local system on the smooth open set, and satisfies particular conditions on the support and the support of its dual. Okay?
So this is the complex that you use to compute intersection homology?
Yes, exactly. That's what I was going to say. Let's continue for pointing it out. So indeed, when this local system is just the constant sheaf, or a shifted version of the constant sheaf, this intersection homology complex actually computes what is called the intersection homology, which is an invariant defined by Goreski and McPherson, which actually restores the Hodge theoretic properties that homology loses when we consider singular varieties. So for example, when you have the singular varieties, we all know that we don't have Poincaré duality anymore, we don't have Arlefshets, we cannot do like a proper Hodge theory. Intersection homology is designed precisely to restore this kind of property, so to restore all the symmetries that get lost. Okay? So, indeed, this is like a direct consequence of a famous theorem in the theory of Berber sheaves. No, let's do like that. Blackboard for short people. So, let me just phrase it for the Hilbert scheme, but for the nested one is absolutely analogous. So, this famous theorem is the decomposition theorem of Beilinson-Bertrand in the linear and Gabber. And in this case, this theorem tells you that if you want to put equality here, then you might need to add some summands. Let me write it down. What do I mean here? I will have some closed, locally closed subset B alpha of our base and some local system on them, and I take the intersection complex. So this B alpha will be supported on strictly less dimensional subvarieties, okay? So the idea is that if I want to extend McDonald formula, I would like this summand here, this dust, supported on the discriminant of our map, to disappear. And indeed, in the hypothesis that we showed, this is actually what happens. Okay? So what we are going to prove today is that for the Hilbert scheme and for the nested Hilbert scheme, indeed, we have just this summand. So we can basically extend the McDonald formula to the whole space. Why am I saying that? So suppose that he's dead. This guy's dead. So now, what happens here? So, if we compute the stock of the cohomology sheaf of the left-hand side at 0, what we get is precisely hi of Cm or Ci of m plus 1, depending on the complex, okay? And this is precisely like the stock of this guy at 0. So to compute this one, I will have to compute the cohomology sheaves of this summand at 0, but these are computable, and we will see how we compute them, okay? So, for the rest of the talk, will be devoted in proving that actually we have this equality, okay? So, what is the problem? What is the main problem in proving this kind of result? Oh, let me say that the result was proven for Hilbert's scheme for the first time by, well, at the same time by Molik and Yoon and Migliori-Schende, but with slightly different techniques than the one we are using today. While for the nested Hilbert scheme, it was proved by myself. Indeed, I think that some of the techniques were already hidden in the Migliori-Schende things that then developed the theory that I'm going to explain. So, the main problem in proving this kind of statement, which are in general called supports theorem. The supports are the variety B alpha that appear in the decomposition theorem. So these varieties B alpha, these supports, are in general really, really difficult to determine. So we need to find a way to restrict the set of candidates for our supports, so that we have to look in like specific subvarieties. At least we just don't go randomly. And this is actually possible in some cases thanks to the so-called theory of higher discriminants, which is due to Migliori and Schende. So, okay, the name is evocative. So, what's the theory of higher discriminant says? So, suppose we have a map F from X to Y of algebraic varieties. Okay? So, we know that we are all familiar with the notion of discriminant. So the discriminant, let me just recall it, will be the set of points in our target Y such that the fiber is singular. So it's the locus where things go really, really bad. Okay? So the idea behind the notion of higher discriminant is actually to refine this notion. So instead of looking at preimages of points, we look at preimages of disk of varying dimension. And what is the main idea? So the idea behind it is that the bigger we take the disk, the more likely the preimage of such disk will be non-singular. Okay? I mean, we know that eventually if we take everything, we will get something smooth. So if we'll get something which is big enough, as we said. So, the idea is that we will take preimages of disk. But indeed, we need to be a little bit more specific about what we mean by disk. So by disk, I mean the following. So I will, so I stratify, by disk I mean that I can stratify my variety, my target variety Y, with respect to the map F. This means that basically that I have a union of non-singular, a disjoint union of non-singular strata, and in each strata the fiber is a topologically trivial fibration. Okay, so it's a topological stratification for the map, and moreover I ask that the strata are non-singular. Okay, so if I'm in this hypothesis and I take a point Y, in Y there will be a unique stratum y alpha containing my point. Okay, if y is smooth, which will always be the case in the families that we are considering today, then by this, let's say that y alpha has dimension k. So by disk, I mean a slice of codimension k, which intersect y alpha just in the point small y. Okay? So here we are in a smooth variety, so we have a well-defined notion of transversality. When I have something singular, I mean, you need to be a little bit more careful. So the idea, let me just say it in words, is that you actually locally embed around y your target variety into some Cn. And then by disk you mean the intersection of y with the germ of a complete intersection T around y, okay? And the codimension will be the dimension of y minus the codimension of this complete intersection. But we don't care today. So now, finally, we can give the right definition of higher discriminant, now that we know what a disk is. So for us, the higher discriminant, lambda I of f, will be the set of points in y, such that, well, there is no I minus 1 dimensional disk. Let me call it the I minus 1 inside y, such that the preimage of this guy is non-singular, and it has the right codimension, meaning that the codimension of the disk is the same as the codimension of its preimage in X. So codim in y is the same as the codimension of f minus 1 of the I minus 1 in X. So if y is smooth, then it's much easier. It's the case when they become more useful, because we can characterize this transversality condition of the disk in terms of tangent spaces. So we can also say that, so if you don't want this to happen and to have the right codimension, it means that for all the linear subspaces that you can have in the tangent space to your point, then of dimension I minus 1, then you have that for all x that lies in the preimage of your point y, then you have that the composition txx tyy of the differential with the quotient with respect to this linear subspace that we have chosen is not surjective. Then, sorry, not for there exist. Okay. So why are we so interested in disks, higher discriminants, and so on? Well, because there is a theorem. I mean, Migliorini and Scende developed this theory because they had a theorem in mind, which turned out to be true. So indeed, what is true is that the supports will have to be looked inside the higher discriminant. So let me just make a few remarks before stating the theorem. So stupid remarks, but important. So the first thing to look at is that lambda 0 of f is nothing but the old discriminant. So the word higher discriminant makes sense. And moreover, we have a nesting of higher discriminant, which is obvious from the definition. So we have that lambda 0 will contain lambda 1 of f, which will contain lambda 2 of f, and so on. Okay? So now, and moreover, the other thing that you can also notice is that lambda I has at most codimension I. This is due to the transversality condition. Okay, so now let me just state the theorem. Perfect. So the theorem, to be precise, is the following. So we have a map F from X to Y. We ask it for it to be proper, just because it's the general setting of the map that the decomposition theorem like that considers. In our case, we had compact fibers, so our map was proper free. So first point. So we have that the theorem is kind of really specific because it tells us that the codimension I supports of the map F are included in the codimension I irreducible components, so the maximal dimensional components of the ith are discriminants. So, and secondly, so to check whether a component is indeed a support, just as a consequence of the proof, can be done on the generic point on the component. Okay, so why is this important actually? So first of all, it restricts the set of candidates for the supports. And in general, the higher discriminant, especially if you have a smooth base, they are much easier to determine rather than the support of the decomposition theorem itself. And moreover, this check allows you to reduce, for example, and we will see, this is actually the way we will use it, to easier family of things. For example, well, we're going to see it now. So, why do you think an example where I'm taking you to? So now, if we want to find a candidate of the supports, so we need to see what are the other candidates B alpha before letting the smooth summon win Miss America here. So, let us just look at the supports of the map pi Hilbert and pi nested Hilbert. Indeed, they turned out to be the same, which is nice for me. So the idea, so recall the settings. So we had our family here. We had the smooth part of the family, B tilde, inside here. And that was pi, and that was pi tilde. So the idea is the following. So we stratify B, so the idea is that we always have to stratify with respect to the fiber, okay? So with respect to the so-called cogenus of the fiber, this is called delta of CB, and indeed this is nothing but the difference between the arithmetic genus of the fiber over point B minus the arithmetic genus of its normalization. Okay? Of course, if a curve is smooth, then the cogenus is 0. If a curve, for example, is nodal, then this cogenus coincides precisely with the number of nodes.
So your diagram here is it? It's that.
Oh, yes. It's
Well, okay. Just
sorry. Yeah, thank you very much. Okay, so if your curve has nodes, this will count exactly the number of nodes. And we define in particular Bi as the set of B in B such that the cogenus of the fiber CB is greater or equal than I. So this, guys, looks actually good as higher discriminant because, so B1 minus B0 is the smooth one, like higher discriminant. Moreover, we have that Bi plus 1 is included in Bi, like higher discriminant. Also, there is a result of Tessier that tells us that the generic points of this Bi are actually nodal curves with precisely I nodes, which is, so here the curve with cogenus equal to I are the biggest irreducible components, and they have codimension I. Okay. And indeed, what we prove is the following.
Sorry, so when you write delta, is the right thing just a normalization?
What?
Sorry,
So
for
I
delta
define
PA
them
of
like
C.
that.
So what is C bar? Is that the normalization?
Yeah, it's the normalization. Yeah. So, yeah, I couldn't use tilde because it would have been misleading. So, proposition. So, if we have that, so we have our family, which is proper, with B big enough. And remember that this implies that the relative Hilbert schemes and the relative nested Hilbert schemes are smooth. Then we have that indeed lambda I of pi Hilbert and pi Hilbert m plus 1. Let me write it this way. I hope it's clear. Are contained in the Vi. Actually, they are equal, but we don't need the equality. Okay? So, why is it so nice? Because it tells us the following. It tells us that we can actually reduce ourselves to check our theorem at the generic points of these guys. So we can actually reduce to prove our theorem when our family, pi from C to B, is a family of nodal curves. Okay? So the corollary, we can check the theorem for families of nodal curves.
Why does it follow?
Because the generic points, so the, fantastic.
So the codimension 1 points are nodal.
The second point of the theorem that I promptly raised tells us that it is sufficient, thanks to higher discriminant, it's sufficient to check whether a stratum inside the higher discriminant is a support at the generic point. Now, the higher discriminant will be contained here. The generic point of this guy is a nodal curve. okay, of cogenus equal to I. So now we can always restrict to the case when we just need to do the checks at nodal curves. But so this amounts to say that we can just prove our theorem there, the support theorem, for a family of nodal curves. So we are almost there.
Can I ask a question?
Yeah, sure.
Is that where planarity enters? Is that where planarity enters?
Yes, exactly. Yeah, to use the CA result, you use the planarity.
Okay, up to now, we didn't need planarity for anything.
No.
We only had planarity, I think, in your title. But that's fine.
Yeah, I mean, at some point, I mean, it's crucial, this reduction here that seems like super easy, like it's a corollary small like that, but it's the one that actually takes the most effort to prove. Also, the big enough part is the one that makes you have a lot of. Also, you use the planarity also for the big enough thing. Now that I think about
You
it.
need to prove that that condition gives the
The right condition is that one, you need the planarity of the curves. So we are almost there. And, well, finally, if we are fed up of support theorem, we can finally forget them. I'm not fed up, but if you are, now you won't see them almost anymore. So the idea is that to finally prove the theorem, so to prove that we have the equality, we will use a Hodge theoretic criterion. So let me just rewrite our equality. So I have R T star n minus 1 q, and on the other hand I have IC of T ID, sum over I, R1 Q, and the same for Hilbert. So the idea is that we want to remember that when we take the stock, this computes the cohomology of our singular curve. If we don't take the stock, it computes the cohomology of the total space. So both of these summand actually carry a mixed structure. And whenever you have like a mixed structure, let me call H, which is the sum over some HI. Whenever you have a mixed structure, you can define the so-called weight polynomial, which is a polynomial in the variable t. So having a mixed structure means that you have a filtration on your vector spaces, which is increasing, and whose graded pieces admit a Hodge decomposition. So you can define this weight polynomial as the sum over I and j minus 1 r plus j e to the I, and the dimension times the dimension of the graded pieces of the filtration W on Hj. Great. I mentioned. And this is a polynomial with integer coefficient. And this is nice because it is motivic. So when H is indeed the cohomology group of some algebraic variety, then you know that you can always do cut and paste. It factors through the Grothendieck group of varieties. And on the other hand, you have a Hodge structure here, and you have a Hodge structure here. So you have well-defined weight polynomial on both sides. So here, you can use a proposition that tells you the following. So again, imagine you have a proper map, again, between two non-singular varieties. So that's why we needed that the total space of our variety, of our family is smooth. And so you will for sure have Rf star Q, okay, the push forward of the constant sheaf of X. And suppose that F is a summand of Rf star Q. Then we have that, so if we consider for any point, we can consider the fiber and we denote it xy, like we did for curves. Then we have that, for short people, we have the following theorem. So if for all y, we have that the weight of the summand f at y minus some sheaf that we don't care about is equal to the weight of the fiber of the Hodge structure on the cohomology of xy, then if this equality holds for all the possible points, then we have that f is indeed the whole Rf star Q. Okay? So, let me put it here. So the strategy to conclude the proof will be exactly to apply this proposition in the case where f is precisely the summand on the left, on the right. So in the last 2 minutes, let me give you an idea of how this equality is proved.
You're okay for a few minutes.
Okay. It will take like
3.
1 minute. Just to give you an idea. So the idea is that to compute the cohomology stock, so we need to compute the stock of the cohomology sheet. So here we will just need basically to compute the weight polynomial of a singular curve. But the weight polynomial, it's easy to compute because we can just decompose the Hilbert scheme of the smooth curve of the we can just decompose the Hilbert scheme of the singular curve into smooth pieces, and it's really easy to compute the weight polynomial of them, and we just sum them up. So here we have to be a little bit more careful. So here what we need to compute are actually, so we need to compute this guy. We need to compute the stock at 0 of this guy. But indeed, what is true is that these are nothing but the monodromy invariant. This is general theory. So I have my TIM for the nested case of H1. So the stock here, I'm on the smooth part. So I will have the H1 of a smooth curve. Let me call it CB. And remember that this is smooth. So McDonald formula holds. Okay? I will have an action of the fundamental group of the smooth part on this guy, and I have to take the monodromy invariant. And the way I do it is really simple because, and I need to compute the Hodge structure, the weight polynomial, but the weight polynomial is easy because we know the Hodge structure of H1, and then we extend by linear algebra, and we restrict to monodromy invariance. So indeed, the idea is that, let me draw a picture. So again, I have, let's say, a curve here with 2 nodes. Here I have a locus in which one node is smoothed out, and here I have a honest curve of genus 2, for example. So the idea is the following then. So up to shrink B, I can always suppose the following. So I can always suppose that the discriminant is a normal crossing divisor. Okay? And it can be written as a union of some di, where di is the locus where the ith node, remember that now we have a family of nodal curves, is preserved. So this one will be D1 and this one will be D2. And their intersection will be the central fiber. Okay? So now I can always suppose also that the vanishing cycles alpha 1, alpha, well, they will be delta, like where delta is the cogenus of this curve. So I will have some cycles, which are the cycles which I shrink, that are called vanishing cycles, and I can suppose that they are linearly independent in H1 of the smooth fiber here. And I can complete them to a symplectic basis, alpha I bi, and the monodromy will be generated by some stuff which I call Ti, which correspond to going around di, and their images inside GL of H1 of the generic fiber, which will have dimension 2 delta, because I need to have as many all as the maximal number of nodes, will be something of this kind. I chose, will be a Jordan block in correspondence of alpha I and beta I, and the identity elsewhere. And indeed, the monodromy is so described by the Picard-Lefschetz formula. And what we do is to actually compute the monodromy via the Picard-Lefschetz formula. And indeed, this basis is particularly useful because, as you see, basically you can decompose H1 as a direct sum of two-dimensional representations. So the linear algebra behind it, it's really manageable in this case. And so in this way you compute the monodromy invariants and their hot structure, and what you can actually see is that you get an equality of weight polynomials, and in this way you prove the theorem. So I'll stop here. Thank you very much.
Thank you, Kanya. Maybe we can have time for one question or two quick questions.
I didn't understand. Why can you assume that the vanishing cycles represent linearly independent homology classes?
Here?
Yes.
Well, because because you can always put yourself in this drawing if you shrink B enough. So you will have that alpha 1. So remember that around the singular point, you always have that your divisor is simple normal crossing. So the nodes that you shrink are different. So here you will have alpha 1, and this is not homologous to alpha 2, for example.
So you are not considering a case in which a central fiber has a bubble.
In which sense? What do you mean by
suppose
bubble?
you have suppose that the normalization has two connected components, and one is P1, say.
Like something like that?
No, but glued in two different points.
Like a double banana.
Yeah. Well, I mean, say for example, two copies of P1.
No, but this is not.
You're not considering these curves, or some
No.
reason. Why not?
I mean, the point is that you need a bigger family for that.
So you can reduce to a stable case maybe, or
No, it doesn't need stable.
doesn't need to be stable.
Okay, here, how do you do it? Let me check how you compute it. If you have a banana curve. No, but here you have just one vanishing cycle, right?
Okay, it's repeated twice, maybe, but
Yeah, you repeat it twice. You repeat it twice, I think. How was it done? I had to think about answer.
Okay, no
It's
problem.
stupid thing. I mean, this curve is okay anyway. But I think that maybe your family must be bigger. I mean, you need to find a way to separate these nodes. So you will have something like that, and
It seems to me that the generic curve in the
the generic curve as just this one.
yes, and then the vanishing cycles of the two singularities will be the same one.
What am I missing? I'll think about it, sorry. No, but you're right, it's a good question with a probably very, very easy answer. Now I'm just... What? Okay, now but there this one would have the genus 2, right?
Yes. Yes.
So...
Yeah, I think every
Yeah,
case
I
this happens is like you have some reducible curves in the
Yeah,
family,
some
but
reducible curves.
we were assuming that it's an
That
integral
the curve
family,
is
so
irreducible.
Ah, okay.
Yeah.
Okay. So your theorem is for families for curves.
No, I mean, okay, the point, okay, now I see what the problem
reducible
is.
curves.
That you can actually prove it for reducible curve, but this is not the proof.
Okay, I see.
Sorry.
Okay.
Thanks. Now, oh yeah, this one is not, of course. I'm an idiot, yeah.
Okay, thank you very much, Kanya, and let's, time for dinner.